Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on pH. Just a really an introduction into pH. I'm not going to be doing any of the calculations today, but I'll just be going through, again, the basics of pH, basics of what some of the mathematical terms would mean. I might have no, the calculations will be in another video. Not intense calculations, just giving you an idea of what the calculations would be like. But there is a bit of maths included in this video, so yeah, and this video I'm expecting to be, it shouldn't be any more than 10 minutes long, this video. Right, so let's just get straight into it. So pH is a measure of acidity of a solution. And the definition, so the technical, I guess really, I haven't got the technical definition here. I could have got it down, but it's not really important. The word definition is, it's really just the concentration of H plus ions in a solution. That's what the technical term of pH is. I don't really know what P in pH means. I thought it's percentage in the past, but apparently not many people actually know what the P in pH actually means. Ask your teacher, but from what I researched, it's actually quite an unknown reason why. But don't need to know about the technical wording of pH. The definition, if they ever ask you what the definition of pH is in your exam, the key term is the mathematical definition. Now, the mathematical definition of pH is pH is equal to minus log base 10 of the H plus concentration. This is it. This is a mark in your exam. They probably usually ask it. If they don't worry about it, but just remember it. This is the one thing you have to know. If they ever ask you for the definition of pH, don't write some words of that thing out. You write the mathematical definition. That's enough as a definition. So the pH of the definition of pH is minus log base 10 of the H plus concentration. In fact, I'm even going to go this. Right, that's in the question you need to know. It could be written as this: pH is equal to minus log base 10 of the H plus concentration, like this. You can write it like that, or AKA, also known as, I never really knew about this until now. I did A-level maths, so I knew about logarithms and all that. And there is a bit of, there's a bit of logarithms in pH. I talked about it in my previous video. There's a lot of maths regarding logarithms in pH. So again, you need to have a great understanding of logarithms and exponentials and all that in A-level chemistry. So you can literally just remember the equations. It's literally just, most of it's just being understanding concentration, moles and volume, that equation, and then relating that to the H plus and an understanding of what that value means. The only time we really need to use logarithms for is the only time we really need to understand how to actually, in reality, you don't really need to know how to fully rearrange. You just need to, if you already know how to rearrange logarithms to using exponentials, that's fine. But really, you can just memorize some of these equations and it's fine, right? But the thing I wanted to talk about here is that, as I said, this is the equation. pH is equal to minus log base 10 of H plus concentration. But one thing I didn't know, even my math teacher didn't really tell me about this, but I guess they could have told me about this. But in logarithms, a capital L actually represents base 10. So you could write minus log base 10 of H plus concentration, or you could literally just write pH is equal to minus log with a capital L, H plus concentration. So the capital L actually signifies that it's a base 10. And in your exam, this is actually the one that they usually put down, but they won't deduct a mark for you for putting this down. That is literally the same thing anyway. But you can just write this instead. I don't know if there's a function in your calculator that allows you to use the capital L, but don't worry about it. Just write, it's much easier just to write minus log base 10 in your calculator. But as I said, there's a reason why we use the log of H plus, and I'll probably go on to this in this video. Would there be enough time? Yeah, it should be definitely written in here. But rearranging the pH equation. So this is the original equation of pH, minus log base 10 of H plus concentration. We're doing the logarithm of the H plus concentration, which makes sense, right? We want to know pH has something, forgetting about the log thing. The pH is something to do with measuring the concentration of H plus in solution. There's a reason why we use logs, but I'll get onto it now. But let's say that we wanted to work out the flip side of H plus, the flip side, right? Say we wanted to work out the H plus concentration, because it's very easy to see how we work out the pH with the H plus concentration. But what if we don't have, what if we want to find out what the H plus concentration is in our solution if we already know what the pH is? Say they tell us what the pH is. Well, we can just rearrange the equation. So you can use the pH of a solution to calculate its hydrogen ion concentration, the H plus concentration. According to the rules of logarithms, you can rearrange the equation above to now, if you know how to rearrange logarithms, you know why this happens like this. But if you don't know it, that's fine. This is another. You don't need to know how to rearrange logarithms. They're not testing you on that. If they ever test your rearranging, it's very basic rearranging. Just divide and multiply, things like that, right? Add, minus, basic bit mass. I guess indices is indices, square roots, squares and square roots. I guess that's pretty easy as well. But if you want to work out the flip side, like rearranging this to work out just the H plus concentration, H plus is equal to 10 to the power of minus your pH. And now it's very important that you have minus in both equations. Minus makes a massive difference in the equation. Otherwise, you get a negative value for your pH when it's not necessarily true. You can get negative pHs, but if you do it in the incorrect way, you're getting a wrong answer. But it is possible to get negative pHs, but this is minus is part of this equation here, right? And it's same as part of this equation here, minus there. So if you want to work at the H plus concentration and you already have the pH, H plus is equal to 10 to the power of minus pH. So these are two equations that you need to know. If they ever ask you about those equations, the definition of pH is just a mathematical equation, minus log base 10 of the H plus concentration. And to work out H plus concentration is equal to 10 to the power of minus your pH. Now, calculation of pH. So it's one thing I wanted to make clear now. As I said in my previous video when I was talking about what was the previous video on Bronsted-Lowry acids and bases. Now, in that video, I talked about I briefly went over strong acids and strong bases and the difference between weak acids and strong acids, for example. This video is going to be just on acids really, but the same principle applies to bases as well. So you have to work it out in a slightly different way, but when we're talking about pH. But if we're talking about acids here, a very, very key principle that you need to understand is that strong acids, the definition of a strong acid is really an acid that fully dissociates H plus ions in solution, right? It fully dissociates H plus ions in solution. Therefore, say we consider 1 mole of solution of HCl, which is, remember HCl is a strong acid, the H plus concentration is also equal to 1 mole per dm cubed. So 1 mole is, we said here, consider a mole, consider 1 mole of solution of HCl. So they told us that the concentration of our solution is 1 mole per dm cubed. But because we know that HCl is a strong acid, i.e., equilibrium is shifted highly to the right, it dissociates, it prefers to dissociate very much, it's a strong acid, we can then assume, because it fully dissociates, that the concentration of H plus is the same as the concentration of the solution. Because there's a strong, we can assume that with strong acids that the concentration, so if they say the solution of, now theoretically when we're talking about it, the concentration of HCl, when we're talking about it, really is the concentration of HCl, we don't really talk about it as being the same thing as concentration of H plus. And now it's a different thing when we're talking about, we consider this HCl a different talking point, as you say, different talking point in terms of concentration of H plus. The concentration of HCl is concentration of your solution of HCl, and your concentration of H plus is a different thing, right? But technically, we assume that because HCl is such a strong acid and it dissociates HCl, it dissociates into H plus and Cl minus, it dissociates H plus ions in solution fully, we can assume that the concentration of HCl is actually the same as the concentration of H plus. We can't assume this for weak acids because weak acids don't fully dissociate H plus ions in solution. So that therefore we can't assume. So let's say a carboxylic acid, for example, right? Let's say ethanoic acid. COOH. We can't assume that the concentration of ethanoic acid, which is a weak acid, is the same as the concentration of H plus, because and definitely isn't that. It definitely isn't that, because we know that ethanoic acid is a weak, carboxylic acids are weak acids. They don't fully dissociate H plus ions in solution. If I was to write this equation here, CH3COOH. That's a terrible reversible reaction sign. right? So this is what happened. This is the dissociation, right? This is not a weak. This is a weak acid, so it's not a strong acid. Therefore, it doesn't fully dissociate in solution. Therefore, equilibrium is a bit to the right, but it's not anywhere near to right as HCl, which is a strong acid. So really, in most of the time, it will stay as this. It will stay as this as ethanoic acid in solution, and therefore there is a way to work out the H plus concentration from this, and it's something that I will talk about in a later video from the concentration. But it's just one thing I wanted to highlight. So if you ever got a question where do you think they didn't give you enough information, trust me, when it comes to strong acids, they have. If you ever want to work out the, I don't know why it's not allowing me to do that. That's weird. That's weird. Anyway, that's weird. But I don't know why it won't allow me to go and rub this off. This is kind of weird. Anyway, yeah, but bringing back to that point, the concentration of H plus ions in solution is equal to the concentration of, so the concentration of a strong acid in solution is the same as the concentration of H plus ions. We can make that assumption because we know it fully dissociates H plus ions. Now, in regards to this, if we wanted to work out, we know the concentration of HCl is 1 mole per dm cubed. So we can assume, because it's a strong acid, that the concentration of H plus is also equal to 1 mole per dm cubed. Sorry, I don't know why there should be a gap between here. Sorry. Makes it kind of confusing. It makes it sound like, so because it's a strong acid, we can also assume the concentration of H plus in solution is 1 mole per dm cubed. Now we put this into an equation, right? We know that the equation to work at pH. So pH is equal to minus log base 10 of our H plus concentration. Therefore, we just substitute our values in. Now we know that we can work out the concentration of pH. So our pH of HCl, of 1 mole per dm cubed of HCl, is equal to minus log base 10 of 1. And that is equal to, if you put that into a calculator, I know the answer is 0, but I'm just going to put it in just for the sake of, if you put that into a calculator physically, if you want to do that at home, feel free, is 0, which is what you'd expect. And acids usually have pHs lower than 0, right? And bringing it back to this here, right? Yeah, I'll use it back here. So the reasons why we use pH. So we use pH because the concentration of hydrogen ions varies massively over solutions. So if you ever think about why we actually use pH, the reason is because the values are so large. And if you understand why we use logarithms allow us to condense a large variety of, or a large range into a smaller range that's more easier to write down. So if you ever got like exponentials, right, an exponential curve, it kind of goes up, and it's hard to tell. It's very hard to kind of pick out specific points. That's why when you're using an exponential graph, you want to put it into simple terms. You use use logs, and you do the same thing in biology when you're doing bacterial growth. You're just trying to make it easier for you to kind of point out that data, make it easier to tell what exact pH you have. It's a smaller range, so it's easier to kind of understand. So because your values could range from between 2 to 3 moles per dm cubed to 1 times 10 to the power of minus 20 or so. And this is a very big scale. So we use a logarithmic one to shorten it. So you can have a negative pH, but it's rare to see ones below -1 or above 15. But obviously between -1 and 15 is a much smaller range and much easier to work with. Imagine using -1 times 10 to the power minus 20. It's not good numbers to work with. Why use really long numbers? And obviously even this is a really toned down value, right? It's usually can be much crazier than that. Why use all these crazy values when you can just use much simpler values, right? So for example, we know that the H plus concentration in water or blood. Well, blood's slightly different, but roughly it's let me use different color. It's water, definitely pure water is 1 times 10 to the power of minus 7 moles per dm cubed. The H plus concentration, as in the H plus concentration of water, of pure water, is 1 times 10 to the power of minus 7 moles per dm cubed. Damn, I don't know why I did that. Right? That's why let me just put this. Let me see if I can put this down here. You know, I'll just leave it there. I'll leave it there. But then you said it's clear to see, right, where 8, 9, 10. If a pH of 7 is 1 times 10 to the power minus 7 moles per dm cubed, then what's 8? Just 1 times 10 to the power of minus 8. And you can see here 1 times 10 to the power of minus 9. I know my handwriting is shocking, but you can clearly see where the trend is here. But it's not, when you get to some of these other numbers, it's much difficult. It doesn't follow the same trend. Well, it does follow the same trend, but it's much harder to work out, and that's why we use our equation. Now imagine saying the pH of something is 1 times 10 to the power minus. It's unnecessary. And you can get much crazier numbers. When you do some of your exam style questions, you get something point something times 10 to the power of whatever, right? To the power of minus 18. Crazy numbers. That's why we use logarithms, and that's just why we put it in this format. Again, that's the end of this video. Hopefully this video was helpful, and I guess if you have any questions or want me to change anything about this video, or didn't understand something, let me know. Hopefully this video made sense though.